All right, it's 10 o'clock, so let's get started. Good morning, everyone. Thank you for joining us today at the Building a Fraud Detection Model with Feature Store workshop. My name is Vicky, and I will be your MC. Our speakers today are Danny Chiao, Esquivel, and Abhin Chhabra. Danny Chiao is an engineering lead at Tecton Feast Inc., working on building a next-generation feature store. Previously, Danny was a technical lead at Google, working on end-to-end machine learning problems within Google Workspace, helping build privacy-aware ML platforms, data pipelines, and working with research and product teams to deliver large-scale ML-powered enterprise functionality. Danny holds a bachelor's degree in computer science from MIT. Esquivel is a solutions architect at Tecton, where he helps customers implement Feature Store as part of their stack for operational ML. Prior to Tecton, Eddie was a solutions architect at AWS. Abhin Chhabra leads the Feature Store team for Shopify's ML platform. Ladies and gentlemen, please join me and welcome our speakers.
Hi, folks. Eddie Esquivel here. So we're going to go ahead and get into the conversation. Basically, Danny and I are going to be going through the material this morning, and then we'll be kicking it over to Abhin so that he goes through the Shopify use case. So I'm going to go ahead and start off by sharing my screen here, and we'll jump right into it. So we're going to, throughout this workshop, basically going to be taking a look at building features for a fraud detection model. And while we're doing this, we're also going to compare and contrast Feast versus Tecton. We know these are two very popular feature stores, feature platforms, if you will. So we'll try to go ahead and distill what the differences between the two are. Tecton and Feast are both well-regarded, well-known. If we take a look at the companies that are using both, we see an impressive list of customers here and users. And there's a whole host of use cases that are really lend themselves to this type of real-time machine learning, where a feature store is key. For example, fraud prevention, as we're going to chat today. But there's also other use cases like recommendations engines, personalization, real-time loan approvals. These are all use cases where something like a feature store like Tecton or Feast would be hugely useful. As a sneak peek, so we are going to maybe speed through the Feast and Tecton piece here to understand what the differences are. But we also, at the end, will have our Shopify friends go over how they've implemented Feast in their stack. Okay. So let's start with Feast. Feast is a self-managed feature store. You'll notice here the blue box. That is really what Feast is interested in doing, storing features and then making those available for real-time inference or for offline training. Tecton, on the other hand, is what we call a feature platform. It's really an end-to-end solution. It is a feature store, yes, but as we'll go through the workshop today, we'll also understand that Tecton tries to go ahead and connect to your data sources, apply the transformation logic that's required to create the feature that you want, and then go ahead and store that and make that easily available. And all the while, there's other things like visibility, governance, and monitoring that are available through Tecton. So once again, Feast, think of it as self-managed open source feature store. Tecton's your enterprise leading hosted SaaS feature platform. So with that in mind, we'll go ahead and jump into the first thing we'd like to highlight, and it's creating features.
Cool. So yeah,
let
me, I guess, present my screen. Cool. Great. So yeah, let me kind of just walk you through roughly the format. So as Eddie mentioned, we're going to be showcasing, how would you kind of build this fraud model within Feast and how might you do it in Tecton. And so if we take a quick look at the example that we're thinking about, imagine you have a transaction stream that's coming in. So like events, each kind of merchant transaction that's coming in, right? You have that as your raw data, maybe in a Kinesis stream. The second step, right, is to convert that into an actual feature. So maybe we're interested in the average transaction amount that this user's had over the past day, right? And we want to compare this current transaction amount to that, right? So that's kind of a feature that we're going to be kind of building. And then finally, we want to make that feature available for inference to detect the actual fraud as it comes in, as well as to train a model, right? So before we kind of dive into kind of how do you configure Feast, how do you make this all set up, I think it's important to understand the bounds of Feast in this kind of diagram. So Feast relies on you to have an upstream kind of data pipeline to compute the features first, and then Feast primarily is responsible for making those feature values available, right? So commonly we'll see community members use combinations of like dbt, Spark, Snowflake, BigQuery, kind of whatever data warehouse compute of choice to kind of regularly compute those features upstream, and then Feast then ingests those in, right? So so on the left-hand side, you can see that this Feast, both Feast and Tecton worked off of a declarative framework, but in Feast, kind of you declare the feature schema of what you're working with. And so I'll dive into kind of the exact code example just in a little bit. But what you see here is on the left-hand side, kind of you declare some sort of feature definition, connecting it to the entities, which you can kind of think of as like the primary keys and to a source. So in this case, it's kind of like combining batch and stream sources into this feature schema, right? And on the right-hand side, once you actually apply to Feast, it's going to make that available everywhere, so that any services that Feast is spinning up for you, it can then understand that. It's going to be able to validate that schema and kind of move it from place to place. So it's going to expose it, for example, in this kind of web UI on the right-hand side. So let me kind of share my window. Bear with me as I guess this only lets me show my entire window. How is this going to work? Technical difficulties. There we go. Okay. So cool. So you can see on the left-hand side, that's the exact same kind of thing that we were just looking at, that feature view definition, which is kind of the Feast concept of kind of the object of the view schema. And then you can see kind of the exact same things here. One additional thing you can see here is roughly how much you configure Feast. So in here, you can see that there is a concept of the registry. That's kind of where we are storing the metadata about all your features in. There's an online store, which we use under the hood as your low latency online storage. And that's primarily used for model inference, right? Because you need to have, you're probably just trying to fetch features for a single transaction or a single user, not trying to fetch a lot of data for training purposes, right? And Feast kind of is also, you configure like your offline storage to be able to pull these massive training data frames. On the bottom, you can see kind of what happens when you run this command called Feast apply. So it's going to commit these definitions into the registry. And in this case, we've actually configured an instance of RDS. So it's going to store that in a SQL database. And on the right-hand side, you can see kind of what I was referring to, the upstream data pipeline. So here I've configured basically a DBT model that's going to be taking the raw kind of event stream and be computing some sort of like daily averages of, so you can see like an average kind of one-day transaction value, right? And so you can here see the actual DBT run. And so let me kind of show you real quick what this all does for you. This is going to give you a Feast UI. So there's a kind of a CLI command that you can run called Feast UI. I forgot to show it in the other kind of terminal, but it spins up for you. You can see this like local instance of the UI server, and it's going to show you kind of just like for each feature view, kind of what are the features that go into it, this whole kind of lineage thing. So, for example, you can go into like a feature service, more jargon, but essentially this correlates to a model, and you can figure out like what features are in that, what kind of feature views power this model, etc. So that is kind of what Feast is all about. And I think that next I'm going to hand it back off to Eddie so you can talk about what this looks like on the Tecton side.
Okay, thank you, Danny. Go ahead and share my screen now. So yes, similar construct here with Tecton. We're going to define everything as code. But if we focus in on the transformation that we've described here on the left side, I kind of give it away there. But if you focus in here, we'll notice that we actually have the transformation logic defined within the definition of a feature view. Okay. And that's important because, again, as we described before, Tecton does try to do the end-to-end feature creation for you. So we will connect to your data sources. We will apply the transformation that you define as code, and we'll go ahead and store that within the feature store itself. So if I go ahead and head over to my code editor here, we can just take a look at a feature view together, and we can just kind of walk through the anatomy of what a feature view looks like in Tecton. If I come over here, we'll notice that, as was indicated, we have the transformation logic. In this case, we're basically connecting to a Kinesis stream. So we're just selecting a few different specific fields out of a Kinesis event. We have the user ID, we have the timestamp, obviously, and then we have a specific column, transaction. What we're going to do on top of that transaction is actually execute a count aggregation. And we're going to do a count over 1 minute, 30 minutes, and then 1 hour. So Tecton is going to update these three features in real time as the events come on the Kinesis stream. The way we go ahead and synchronize what's on our local notebook with what's in Tecton is via the CLI, similar to Feast. We'll just basically do a Tecton apply. If you're familiar with Terraform, similar concept. You do a Terraform apply, Terraform plan. We'll do a Tecton apply in this case. The big difference, however, is that, yes, we are spinning up infrastructure on your behalf, but we're really almost defining data pipelines as code here. So we will be executing these data pipelines on your behalf. And if I head over to the UI, I think that can start to make sense. So now I'm going to head over to the Tecton UI. I'm going to go back to this user transaction counts feature view that we just created. I'm going to click on the pipeline view. And if I scroll down, we'll notice that we have the Hive data source registered here. We have the data source. We have the aggregations that we're actually computing, and we're obviously storing those in both the offline and online store. So when you do a Tecton apply, what Tecton does in the back, behind the scenes, if you will, is go ahead and spin up that Databricks cluster, spin up that EMR cluster, spin up or execute that Snowflake query on your behalf with the transformation logic you defined, and then store the output of that into Tecton. Okay, so that's what I wanted to go ahead and highlight here. I will send it back over to you, Danny.
Cool. So back over here. Sorry. So so the next kind of step is kind of, we talked a little bit on the Tecton side, like how you manage these data pipelines. But I wanted to dive a little bit into the differences between how Feast and Tecton kind of handle that. So on the Feast side, why do people use Feast for this? A lot of it is actually about abstraction. So it's about how do you decouple ML from the data infrastructure. So what I mean by that is when you're fetching a feature in real time, often you have to kind of figure out, like, where does this feature come from? Let me kind of make the right RPC. Let me kind of pull from the right online store. Let me worry about, did it come from, which original data source did it come from, right? And so Feast provides kind of this middle abstraction layer that makes everything consistent. And that's going to be really important, as we'll see soon in, how do you simplify this entire ML stack? But let's jump back to our original example here of how might you compute this average daily transaction amount, right? So when you first start, you might kind of think about, okay, let's just take this raw Kinesis stream that we're getting in. Let's do some Spark or Flink streaming transformations on top of that and kind of ingest that into Feast, right? One thing that you're going to definitely have to do is orchestrate this pipeline. So because you're powering this, real-time model, you can't really afford to have, lapses in freshness. Like if you just suddenly stop publishing features, you're going to have incorrect model outputs, right? So you need to have a certain orchestration layer here. And, people can choose kind of whatever they want. Sometimes you'll use like Airflow, maybe not always the best option. People will use kind of various options such as like Databricks or workflows as well. But that's going to get that initial feature into Feast, right? But we're not done yet, right? Because with just a stream, you're going to be limited to the kind of your TTL for your essentially like how much data you're storing in your queue, right? And that's usually on a much shorter time frame, like maybe like a week or something like that, right? You really need to be able to get all your users' features that's happened kind of over the past however long, like years, right, of data. And so that's where you actually need to have a second kind of set of features coming in from your batch data, right? Usually you're going to have a raw archive of your streams, and so we can then it's on you then to essentially do what we saw in the first section of using tools like dbt and Airflow to orchestrate transformations, and then finally kind of get that into Feast, right? And what you'll see here on the right hand side is kind of backfilling. So right, like we started with the streaming features that came in. That's going to give you maybe like a week's worth of features, right? You need to get all the rest of those features in from the past year, and that's what we call backfilling, right? So how do you backfill from that? Feast will help you orchestrate that with that same schema, but still relies on the user, so and you in this case, to actually orchestrate the logic but call into Feast SDK methods, right? And so all a little bit abstract. I'll show you kind of exactly kind of what's happening and the actual code behind this. But in short, right, to power this real-time ML model, you need to set up kind of almost like 3 different kinds of orchestration loops, as well as the streaming transformation and the batch transformation. And where Feast comes in is to kind of decouple that ML from the data infrastructure. So let me share my let's see. Cool. So I think the most important thing to look at here is the kind of Airflow DAG here on the right hand side. So let me kind of just close out this stuff to make it more clear. Oh, you see my VS Code, right? Cool. So what you're going to see here is kind of a simple DAG. It's going to be connecting dbt, test and dbt run into Feast materialization. And so that's kind of that backfill logic here, right? That's moving data from your offline store into your online store. Why might you want to kind of have this in the same DAG? It's really that you want to Feast is going to be kind of regular materializing, say like on a daily basis, and pulling from your offline data store to move into the online store. But it's not going to really work unless you make sure that that transformation's already happened, right? And so that's kind of why in this DAG, I first have done dbt's kind of transformation, and then I run Feast materialization. So you'll see here kind of like, here's how I define kind of a Feast instance in code, very similar to that kind of YAML file that we saw originally. And then you see that, it's quite convenient that you can just run like store.materialize. And this method actually gets a little bit more flexible. You can say like, let me just materialize this feature view, for example. But the key thing here is that you don't need to think about where it's coming from, right? You don't need to care about kind of whether it's which table is coming from. Kind of Feast will handle all that logic for you, right? So I can then kind of show you the actual Airflow kind of DAG, and then I'm also going to show you kind of how we call into it from Feast. So yeah, this is kind of just that exact same DAG already visualized. You can see that it's already kind of succeeded with kind of those 3 different steps, right? If I jump over here into Databricks, kind of which is where I've set this up for, you'll see kind of that exact same definition to instantiate Feast. And over here, I've done kind of the same kind of materialized step within a notebook instead. So you can see kind of this is the actual, it's pulling features from that transformed data frame and kind of moving it into the online store. That other kind of, then we also see the other kind of streaming aspect of this, right? And so you'll see here, I'm reading from the Kinesis stream, I'm deserializing it, and I ingest it into Feast using Spark. And this is all happening kind of outside of Feast, right? Because Feast is only processing the transform functionality features. And so here's kind of really like where Feast comes in, where you're able to push in the values of already transformed into kind of using the store.push mechanism, right? And what Feast is going to help you do is kind of unify the features that are coming in from here as well versus the features that are coming in from your batch source as you're kind of materializing at a regular cadence, right? So that's kind of roughly how you manage data pipelines in Feast. And I'll hand it over to Eddie to show you kind of what that looks like on the Tecton side.
Thanks, Danny. So yeah, as was indicated, Tecton is going to go ahead and manage that end-to-end pipeline for you. So that what that means is basically you don't have to create an Airflow DAG. You don't have to worry about executing the job, making sure the job runs successfully, and then working with the result that was stored in the feature store. If I head over to Tecton, I can kind of highlight also the other thing that was interesting in comparison to Feast is that Tecton will manage the backfilling for you as well. If we take a look at this transformation again, there's a Kinesis stream, but there's also a corresponding Hive table that you can connect to. Okay, so we'll use the Kinesis stream for the latest and greatest events, and we'll use the Hive table for that sort of batch, as a batch data source for backfilling. So if I head over to the feature view again, we'll notice again the two data sources are registered here. If I click on the materialization tab, I think this gets a little easier to understand. One of the jobs that's running on your behalf is that stream, Spark streaming job. But then there's also the additional batch jobs that are kicked off that are basically doing the backfilling. And those batch jobs are basically connecting to your Hive table, reading in a window of data here, going back as far back as you need to go back with your backfilling, and then going ahead and storing that result into Tecton. So just something to keep in mind as you think about Feast and Tecton. There is basically the easy button, if you will, for feature creation that you'll find with Tecton. So kick it over to you, Danny.
Cool. So yeah, the last bit of this is how do you actually retrieve features? How do you kind of serve these features, right? And so both Tecton and Feast actually have a fairly similar API on this front. It's going to be, a simple kind of get historical features to generate training data, and get online features to generate these kind of online features. And so, and in both of these cases, you don't need to think about where that data came from, right? It's kind of the same simple, consistent API to retrieve from both cases. I think that's, yeah. So let me kind of show you what that actually looks like in my actual Databricks notebook. So I think, yes. Yeah, so keep in mind, so I'm going to show you kind of how this happens in a notebook. Often, though, when you want to power this kind of model inference, you're often embedding this logic directly into, say, your Python server, or there's also kind of a Java equivalent of this on Feast as well, right? But first, what we see on the left-hand side is kind of how do you generate training data, right? And so the first thing that you need to generate is kind of this, well, we're calling it this entity data frame. It's really, what is your label of set of events here that you want to kind of append new features into, right? So in this case, you can see that I'm pulling in kind of transactions that they've come in, as well as an is fraud label, right? And I'm passing that into Feast. So store, you can see that I've initiated that same kind of feature store object, and it's going to kind of generate, pull all the rows from this table, generate that kind of data frame, and then append all the user features that are point in time correct, as of the timestamp that have occurred in this kind of entity data frame, right? So you can see that in this case, you can see the original kind of values that are passed in, and then kind of the additional features that we defined earlier that are all being pulled in. So in this case, it's actually a little bit simpler of a situation where we have a single feature view. Where it becomes very useful is where you have, often a lot of different groups of features, a lot of different iterations. Feast is going to join all those different groups of features together in a point in time correct fashion, right? So that's kind of, how do you generate a training data frame? It's also going to be used if you want to do, say, batch scoring. So you have say a weekly cadence you want to, pull the features and actually run inference on that, right? You can do the very exact same thing, but instead set this to be, the current timestamp as opposed to kind of this historical timestamp. On this side, you can see kind of the Pythonic way of accessing it. So as I mentioned, there's kind of other ways. There's like an HTTP API that can expose as well. But here you'll see that we're calling to the same feature service, or like the model, the groups of features that you need for this model. And you're passing in like the user, right? So there's no timestamp associated. You want the latest version, the latest feature values for that user to power this model inference. And so you can see that when we actually print that out, it's going to give us some object. And if we print that out, it's going to be kind of, exactly kind of what we expected. The user ID we passed in, as well as the corresponding latest feature values that are resulting from, the stream ingestion or the batch materialization, right? So that is kind of how it works in Feast. Let me hand it back to you, Eddie.
Okay. Yeah, so I will similarly go through what the process is for retrieving features out of Tecton. Obviously, the two different access patterns are for training and for inference. So for training, we're going to use the Tecton SDK. Basically, step number one is go ahead and create what we call a spine. Basically, it's a data frame that has all of the entities that you're interested in retrieving, along with the corresponding timestamp that's interesting to you for your model. Once you generate this, typically by connecting to a raw data source, again, through the Tecton SDK, you can create your spine and then feed it into a get historical features method. You'll pass in the spine. However many features are associated with this specific feature service for your fraud model, Tecton's going to go ahead and make sure that all of the point in time joins are done correctly. So as we noticed, you passed in the spine up here. On the return, you get the spine back, maybe any labels that you associated with that spine, as well as all of the underlying data that you can then use to train your method. And then from like Tecton's perspective, that's really where our contract ends. We give you the data frame, and you can go ahead and use the framework of your choice to go ahead and train your model. You can also host your model however you'd like. We're not opinionated with regards to how you train or serve your model. And then lastly, similar to Feast, you go ahead and have that endpoint for online inference. If you take a look at this, basically HTTPS request, you'll specify the feature service name, pass in any entities that are associated with the underlying features. Maybe you have some on-demand data that you need to featureize in real time, for example, within the context of a fraud model, stuff like the transaction amount or the location of the transaction, the time of the transaction. This is all interesting data that you can then featureize. So basically, you'll make a call to Tecton, and you can go ahead and pull down your feature vector for inference. And this is where Tecton also shines in terms of SLAs and SLOs. We have a guaranteed SLA of less than 100 milliseconds for this specific online inference request. So you can imagine we have customers that are doing, tens of thousands of fraud, inference scores per second. And that's the type of release scale that Tecton can go ahead and achieve. Okay, so I will now kick it over to you, Danny.
Cool. So let me just kind of wrap it up so that we can kind of get over to Abhin real quick. So where did I go? Cool. Yeah. So let me just kind of quickly recap. So yeah, like if familiar with this diagram at this point, this is kind of what I described as the end-to-end kind of feature lifecycle for Feast, right? So you have your raw data, you transform it, and then by the time you get to Feast, they're already transformed, right? So in kind of a simpler manner, Feast expects the transform features as input, and as output, it outputs transform feature values as well for real-time serving or model inference, right? And there's kind of all these different orchestration components here. And Tecton's kind of essentially going to be building all these pipelines on your behalf for you, right? One thing I want to kind of just clear up, though, is people commonly ask, like, is Tecton built on Feast? And the answer is no. They're actually just frameworks that are compatible with each other, right? And built on a very similar ideology, but under the hood, it's very, very different logic. And so kind of like, when do we see kind of, people most successful with Feast, and when should you use Tecton instead? Usually, at least what I've seen, is that people turn to Feast if they and particularly don't really need any kind of help managing their own feature store. So they have an existing fairly large ML platform team that has a lot of DevOps experience. They need a fairly customizable solution because they have just like fairly long tail needs or specific to a large like their kind of individual enterprise, right? And the biggest thing I think is really that they don't really need any help with existing streaming or real-time feature pipelines, right? And so this is pretty common. Like if you're trying to take an existing in-house feature store and kind of just like or feature pipelines and refactor that, right? You already have the production working pipelines. You just want to decouple that ML from data. Whereas kind of on the Tecton side, right? Tecton's going to manage a lot of this overhead. And so this makes a lot of sense if you have, an existing feature store that just like it's a ton of pain to manage. You don't want to continue to staff several engineers just to keep existing models running, right? We also see people coming in if they need just mission critical reliability and scalability. And so, like not needing to think about like on-call rotations and kind of coming in to ensure that your data is still freshly available, right? And then kind of, in contrast to Feast, what those streaming and real-time pipelines, Tecton's going to automate a lot of this for you, right? And kind of have those production-backed SLAs. So it helps a lot with that front if you need that help with streaming and real-time feature pipelines. And then one key kind of difference in terms of just like technical requirements is Feast today kind of supports on-prem, GCP, Azure, and AWS, right? All the usual suspects. Whereas Tecton today kind of primarily is on AWS, right? And so, but soon to come to GCP and Azure. So yeah, that's kind of like roughly what I want to get at here. Oh, and one final kind of call out is that Tecton is actually quite focused on the collaboration aspect. And so whereas Feast is just targeting the engineer and helping them build out an ML platform, Tecton's kind of really meant for not just the engineer, but also helping data scientists and kind of other personas within an organization all collaborate on ML features. So yeah, that's I think all we had for you. And then let me kind of hand it over to Abhin to kind of dive into a case study of how they've built a platform on top of Feast.
Thank you, Danny. Thank you, Eddie. I'll be going over how Shopify uses Feast as its feature store. The project is called Pano. We call the feature store Pano internally. So anytime you hear Pano, think Feast, but like a shallow wrapper around it. My name is Abhin. I am the tech lead for the feature store of the ML platform at Shopify. I've got some emojis showing things I do outside of work. Oops, sorry about that. Cool. So I'll start with the business case for a feature store. This applies to Pano, but this could also apply to your org. Essentially, feature engineering is a lot of work. It takes a lot of work to get rid of all the idiosyncrasies in your data. Common problems are like, what do you do with null values? What do you do with negative values? Whatever, you understand the point. There's a lot of idiosyncrasies with the data, and teams often find themselves repeating the same work across multiple projects. It would be great if that work could be shared. My mental model of a feature store, Pano, Feast, whatever, is it's a marketplace. It's a marketplace of features. There are producers of features and there are consumers of features. And the broker in the middle that facilitates this exchange of features is the feature store. And that kind of allows teams to share features, but an obvious question then arises, why bother? Why not just have teams access each other's features by directly querying the data warehouse? So if your data warehouse has tables, why don't teams just like access each other's tables? Well, you could do that, but there are some downsides, and you will miss out on a lot of the upsides of having a broker in the middle to facilitate this exchange. There will be some issues with running it in production reliably, and I'll go over them right now. A broker like Pano can enforce standards on datasets. Feast, for example, really pushes you to have type 2 dimension datasets, incremental datasets that have a column with a timestamp-based version that allows you to time travel. And this is really good. This is really good because it allows you to reproduce your ML jobs. A broker like this can also automatically make sure that the data is available both in online and offline contexts. As you saw earlier, when you do a push operation with Feast, you can have it go directly to your online store and your offline store. Offline store is great for historical retrieval. Online store is awesome because if you're doing real-time inference, you need a low latency feature serving solution. It's really helpful to have that automatically be set up for you. A broker could also validate your datasets. It can validate your datasets using some easy to understand rules. So if you're shopping around for features, if you represent a ML project and you're shopping around for features in this feature store, you can kind of look at the guarantees that are made available to you by the feature store. And you can rely on these guarantees rather than just evaluating them yourself, checking them yourself. You can just rely that the feature store is making sure that these guarantees about various columns are true. You could watch the data. You could have this broker watch the dataset for drift and alert you. It could help you figure out if the statistical distribution of your training features is significantly different from your inference features and alert you on that. It could alert you if the dataset being consumed by your job is stale in either of the online or offline contexts. And when you're looking at features in your ML project as a consumer, looking at the feature store, the broker could help you understand the quality of features before you couple your model's quality to the quality of the features that you find in the feature store. It could help you discover the quality of these features ahead of time. How stable has this feature been historically? How has this feature been drifting over time? How many disruptions has this feature had? What's the average time to resolution for these issues historically? Where do you tell people about how to file issues? How many unresolved issues exist, et cetera, like how fresh is the data? There's a lot of information that can be made available to you as a person shopping in this store of features. To be clear, Pano currently only implements the first two of these requirements, but we are rapidly working in 2023 to basically implement all of the other ones as well. To go over Pano's goals, Pano's vision, and again, this applies to any feature store in any org, I imagine. If you want significant sharing of features between projects to save them time and effort, you need to develop trust in the features that people are consuming and trust in this marketplace, Pano. The goal is also to improve the return on investment, not just by saving people time in doing feature engineering, but also by improving the overall quality of the features. The goal is also to improve the reliability of these ML models. Data quality issues with features are usually a leading indicator of model performance issues. And this can help you improve the time to detection of issues by augmenting actual model output monitoring with monitoring of the features themselves. The goal is also to improve model performance by improving ML feature quality across your org. The idea is to surface quality metrics to users when they're shopping for features and to bias people into knowing which features are the highest quality and using them. I'll go over quickly the bigger picture of the ML platform with some emphasis on Pano. Let's start from the bottom right corner. You've got this foundational layer called Merlin. Merlin is Shopify's ML platform. It's been blogged about, talked about a lot. It's based on Ray, which is a distributed computing framework, and it heavily makes use of Kubernetes. Essentially, this Merlin API layer is able to give you ephemeral Ray clusters, which allow you to distribute your compute. And above that, I've got like an example of a ML training pipeline. The steps inside aren't actually that important, but quickly going over them, you first extract the data, do some preparation, train, evaluate, validate the model. When the model's all ready to go to production, it exists in the model registry. And then above that, you've got some model serving. So you can serve your model for both batch contexts, where you're getting historical, well, not historical, you're getting batch data for inference, and online, where you're getting like low latency, you're doing real-time inference. In both the model serving part and in extraction of data, you need to get that data from somewhere. And on the left side, you see boxes indicating the data warehouse. So the data warehouse at Shopify contains a lot of things. That's what the ellipses represent. But the thing I wanted to focus on is BigQuery, which is our offline store for Feast. So this is where you get historical data. And the box above that, you see Pano. Like I said, Pano is a shallow, thin wrapper around Feast. It's got its own feature repo, and it relies on Bigtable for online serving, for low latency serving. Both the model serving and the data extraction are able to get data both from Pano and directly from the data warehouse if they want. So you can kind of have some of your data coming from the feature store and some directly from the warehouse if you want. Well, there used to be an image here. Not sure why that's failing. Oh, there it is. So quickly to get this out of the way, what is Pano? Why is it named that? It's named after a character called Panoramics. It's part of our family of wizard characters, after which we seem to name a lot of ML components at Shopify. The other one you just heard was Merlin, also a wizard character. We've been working on Feast, on Pano, on and off for 1.5 years now. And like I mentioned earlier, it's built on top of BigQuery for the offline store, Bigtable for the online store, and to materialize data, which is to take the latest data from the offline store and make it available in the online store for low latency serving, we use Ray to materialize as the materialization engine. The purpose is to massively parallelize the actual materialization operation. Diving a little bit deeper into Pano, this is a very typical setup for Feast installations. Let's start from the top left corner. You've got a GitHub repo containing all your feature views, feature services, entities, all the Feast objects. When you make a pull request to that repo, we basically automatically have a comment that shows up that tells you what the Feast plan is. So what operations are going to be performed on the registry and some infrastructure operations if you were to merge this PR. Once you merge the PR, your normal CI/CD processes, one of them does a Feast apply to the registry. So the Feast registry is, I guess in our case, a file in GCS that stores the state of like all the feature views, feature services, entities, etc. And the two Python processes you see are just arbitrary batch and online processes. For the batch process and the online process, you fetch the registry from GCS. For the batch process, we query BigQuery for all the offline features. So the call you saw from earlier, I think Danny showed, was a get historical features. And in online processes, it's get online features, which are served from Bigtable. And you've got, like I indicated earlier, a materialization process that's scheduled via Airflow and run on Ray for the massive parallelization of fetching the newest data from the offline layer and writing it to the online layer, Bigtable. I want to go over some of the challenges we encounter and some of our learnings, and hopefully they can be useful for you as well. The first challenge is in our setup, we don't control the data sets in the offline store. So if I go back to the diagram, BigQuery here is part of the data warehouse. The pipelines that write data to it are outside of our control. They're existing infrastructure at Shopify. Pano doesn't maintain those transformations. People just register the tables feature views in Pano. So we don't really own the processes that write to these tables or the tables themselves. Some of the problems with not having ownership of these tables is that, for example, the table schema might not match the schema that the user told you about in the feature view description. The lesson from that is CI checks are important. We have a CI check that we added after learning about these issues that compare the schema. The other lesson from this is if you have a data lineage system, it's to integrate into this data lineage system early on, so that when people are changing schema, evolving the schema, they know of all the consumers of these tables, including your feature store. Another issue that crops up is the producers of these data sets might actually remove these tables without notice. Again, that can happen because we don't own these tables. The lesson is the same as the earlier one. Integrate into the data lineage system so people know that you are a consumer as well. They reach out to you, you let them know that that is going to have effects. If possible, if there are dataset lifecycle processes in your org for when datasets are deleted specifically, it would be good to hook into those to kind of avoid these situations. Another challenge is that the idea is to have teams share a lot of features, but we haven't been seeing as much feature sharing as we had hoped. And there's a couple of issues with that we've encountered in some of the lessons. So first off, teams might not think to search through your feature store before they start feature engineering. They might just go ahead and assume that they have to do all the feature engineering themselves. A lesson from this is to, if you have some data discovery tools in your org, integrate into them early. We didn't do that, and that led to like a lot of teams unnecessarily duplicating effort. And this is something we're currently doing, and this should be done actually quite soon. I was actually hoping to have a screenshot of that available for this talk, but running a little bit late on that. But that's an important lesson and could help you avoid the same mistakes. And be aggressive with promoting the feature store internally. As much documentation, internal blog posts, internal talks, whatever you can manage. And this is also like an ongoing process for us, because if people don't know about the feature store, they're just gonna duplicate effort. Another issue is that teams might not contribute the features back into the feature store. So first off, like a technical issue, teams might not even consider creating type 2 dimension incremental data sets, where you have like historical versions of your features. For this, I guess the thing to do is to encourage these incremental data sets through documentation, to explain that incremental data sets have a benefit, that they allow teams to reproduce ML jobs, and that helps with troubleshooting and debugging. The other is, once a team has engineered some features for themselves, what incentive do they have to put in the extra effort to register these features into the feature store? That sounds like additional work. So in general, like all teams are of course good. Everybody wants what's best for your org. Everybody wants to put in the work. But we found that it is helpful to shift the ROI calculation on whether or not they should contribute back to the feature store by providing functionality that just doesn't exist outside of the feature store. So in our case, we're working on making sure that like the data is automatically available in the online store. We're working on making sure that the data gets validated. We're going to be working on drift detection for online feature serving. All these features are things that people wouldn't get outside of the feature store, which incentivizes people to register their features, which then helps other teams use these same features and kind of has like a whole snowball effect of helping everybody. Lastly, I want to go over where we're headed. The first thing we're currently working on it, is data quality monitoring. We want users to be able to declaratively specify constraints on features. Constraint would be like, I expect this feature to never have any nulls, or I expect this feature to be a float that is never negative, or if it's a categorical feature, I expect it to every value to be part of this set, etc. Or range checks, whatever, declarative constraints on features. And this will help improve the quality of ML features, because we'll be able to verify that those constraints are correct and alert people on it. We'll also be working on monitoring data freshness. So if for some reason a pipeline has stalled, we want to be able to detect that. We want to be able to detect how fresh the data is in the online and the offline stores and alert people on that. The next item is better integration with internal data discovery tools. This is something I mentioned earlier. This will make it easier for data scientists to find existing features and to reduce feature engineering effort, duplicate feature engineering effort. The other nice thing about it would be that this provides us an avenue to surface a lot of metadata about features like quality metrics, constraints, freshness, SLOs, etc. Any metric we can think of that would indicate the quality of the feature. And lastly, we're going to be working on, I think what Danny showed earlier with the push method on the feature store, where you can push data to both the online and the offline store simultaneously. And that's going to increase the data freshness for our online store today. Today, our online store relies fully on the materialization process, which takes the latest data from the offline store and copies it into the online store. That has certain limitations on how fresh your data can be. If you're able to directly write to it from a streaming pipeline, of course, you get fresher data. And a lot of teams have been asking for that. So yeah, that's where we're headed. Thank you for listening. I guess Danny and Eddie would probably come back on and we can go through the questions. I guess the first question is for me, I think. I'm just going to read that out loud. What would be the advantage of using Pano compared to the feature store of Google Vertex AI? So at least for the Shopify angle, and maybe Danny can also talk about this because you've probably looked into Feast versus the other products. From our point of view, we felt that the specific vendor products were very integrated into the rest of the Vertex AI stuff. We have existing systems that we didn't want to wholesale replace. And we felt that, like in our case, A, we wanted to have more control over it. B, we wanted to just build parts, just like adopt the feature store component and not buy into everything else wholesale, I guess. Danny, do you have an answer for?
Yeah, I think my answer is kind of in a similar flavor. So part of why people often choose to use Feast is because of how pluggable everything is in Feast. And so Feast will define kind of like interfaces for everything. Like, here's an interface for an online store. Here's an interface for an offline store. But at the end of the day, you control everything, right? And so you can say, maybe for this model, I want to use like, Bigtable. Maybe for this model, I want to kind of add a cache in front of that, right? And that's all possible kind of within the Feast framework. And I think that level of customizability is not usually found in vendor specific options. I haven't looked as deeply into Vertex AI. But that's kind of my general, what I think is generally true. And of course, like there's also the open source angle as well, right? And so, which is often a big kind of a contributing factor. Like you want to be able to kind of see what's happening. If you see a bug, you can fix it yourself. If you have a contribution, you can collaborate with other community members. So I think a lot of folks get a lot of value out of that as well.
Yeah, to some extent, I feel like the value or the calculation on this depends on sort of your size and how much complexity you're willing to take on. There are advantages to having control, but of course, that's not for everyone. I wouldn't have personally, if I was like in an org of, let's say, 10 people, I would prefer to go after a managed solution. But in a larger org, you want the control. Yeah. I guess the second question is, have you provided training on Pano to the data scientists at Shopify? I'll go with Shopify. I'll go with that being a typo. It's a common typo, no worries. Yeah, so we have a lot of documentation internally. We have, I guess we don't have as many like workshops or video tutorials or anything like that, but we do have tutorials that are written, a lot of documentation. Yeah. Let me know if I didn't answer your question, and please feel free to follow up, but I'll move on to the third one. Oh, I see. Yeah, I kind of covered that on the slide where, yeah, it's just not part of like the, I think it is a little bit of like searching through documentation and kind of trying to understand the workflow of data scientists. Make sure you interject in the right places in the docs. So if there's some documentation on like how to build ML models, some overall docs like that, I think it's helpful to interject there and kind of talk about like looking through existing features before embarking on like feature engineering. And I think that's like an ongoing pursuit where you're kind of just interviewing a lot of data scientists and finding out like why they chose or why they didn't know about it.
Yeah, I can speak a little bit more to kind of what I've seen as well, which is that often, especially data scientists are not as interested in kind of a lot of the value adds of a feature store, like kind of the, if you want to say, hey, this is going to be automatically available online, that kind of before wasn't really their problem. Anyways, they kind of are used to often just like throwing it over to the platform engineers, like, hey, can just like make this available online, like make it ready for production, right? So it wasn't really their problem to begin with. And there's also, I guess, like on the, I think there's still kind of this gut like instinct that like, hey, my problem was fairly unique to my situation. Why would anyone else have solved this problem before, right? And you tend to, because data quality is such a big focus area, you tend to also be distrustful of other data sets that you're using. And so if you're going to be spending a lot of time data cleaning anyways, you might as well just start from scratch, right? So I think that's kind of, right on with where Abhin is saying, like data quality, I think is a really big kind of aspect of this as well.
Yeah, we find it helpful. Like when I look at most teams that are adopting features from the feature store, they tend to be ones who came in looking for other things, like data quality monitoring or the availability of features online. And the benefit from reducing their work is like then shows up. But I think it's a cultural change thing, and the industry is also like slow to change. It's not something that's like covered in a lot of places where you learn about ML. So yeah, it's a slow process of shifting culture, I guess, a little bit.
The other thing I have seen kind of resonate well, and we should move on to other questions as well, is like scaling up training data generation. And so often, like if you're kind of doing like larger joins, or if you're trying to do like aggregations, often that'll just like slow down, say, data warehouses to a crawl. And so you'll need to kind of build in, say, like partial aggregations and whatnot. And so I think we've seen like if you can build in some sort of optimizations into that flow and help them scale up automatically, that's often a reason to kind of use a feature store as well.
I guess we'll go through the next question. Where do feature stores fit into the lifecycle with data labeling? Can these tools, or does Pano, have any insight into best practices for labeling features and then feeding them back into the data pool and then update the feature stores? You mentioned before that the data from feature stores can be used for training, so there must be some way. This seems more feast specific, I guess, than specific to Pano. Dan, do you have an opinion on this?
Yeah, so usually I think this is going to come down to like a per problem basis. So like sometimes your label is inherent in the actual action itself, right? So you can kind of do like, just like look forward for like the next thing that happened, or look back, right? So it becomes a little bit easier to handle. Sometimes it's separate. And so feast, I don't think like really owns any part of the lifecycle. It kind of relies on you to say, here's like the entity data frame that you're passing into Feast, right, and join in the labels that you have, right. So that's kind of the stance on that. And usually, I think you'll have some sort of way to join them, right. You'll have like a here's the entity, like the transaction ID or whatever, and the corresponding label at a certain timestamp, and you can kind of join that in, right. So yeah, I wouldn't say that it's handled in a very first kind of party way. So
we also see on our end, some teams do store their labels also in the feature store. But again, it's up to the teams to decide how to make that happen. That's not a core offering of the feature store itself.
Yeah,
but it is helpful.
Sometimes I've seen kind of ML platform teams actually build wrappers around this. And so if you register like a certain thing as your label, right, you can tag that maybe as like a metadata in Feast. And then what teams will do is they'll regularly kind of generate the entire training data frame, including the label, and then export that to say like a BigQuery table, right? And then the data scientists, they basically just say, hey, use this kind of output table that we're going to just be regularly refreshing with the features that you register.
Right.
So
that's cool. I guess the next question is more generic to feature stores, but how is feature engineering done in the feature store? I guess maybe this is more for Danny, but I know that that's like a difference between Tecton and Feast that was discussed. Maybe Danny can go into it.
Yeah, so I think I've seen different takes on this, right? Like we kind of walked through in this workshop, like using DBT as kind of one mechanism to do that, right? But I think Feast is still fairly early on. There is kind of some early work around like on-demand transformations within Feast, but typically I think a lot of teams already have their existing pipelines that already do feature engineering, and so it hasn't become like a top priority thing for the community to kind of work on. But certainly there's interest in the community to build some functionality on that front. I think if you're trying to build in feature engineering, like similar to what we just talked about, right? Data scientists are often, they're not really incentivized to encode a lot of this feature engineering logic within the feature store, right? So that's it's actually more of an incentive for the engineers to say like, hey, if we can convince you to like write it in this way, then we can kind of take it over and kind of operationalize, productionize some of these feature values, right? And so I think that's the trade-off that you're making. And Tecton's stance on this is like, hey, like actually, if you just write it in here, it's just gonna be available everywhere, and you get all these additional benefits, right? So similar to where Abhin's heading. But yeah, that's my kind of not so crisp answer on that. I think we're kind of, I think we can still go over a little bit, but just want to say that we are 3 minutes over. Next question is, any advice on how to narrow down features to collect or process from the lens of the size and usability of the data store? I guess my initial take on this is, one version of this, like people often have a bunch of data sets already created for, let's say, like analytic purposes, and they're interested in like, how do I convert that into features? And usually I've seen teams actually split that out, like kind of identify, here are the ones that I want to kind of power a machine learning, because that's where you care a lot more about like, having those features readily, like continuously reproduced. You care more about the data quality of that on an ongoing basis. And so usually I do see like, a split in like how you handle one set of features versus the other. But I don't know if that's exactly what you meant here. I mean, there's also kind of another angle around like feature importance ranking that you can do as well, right? Where, you can like throw in a bunch of features and then prune down kind of what you don't see as important. And I think there's like standard mechanisms for doing that, right? Like,
yeah, on my end, to be honest, I haven't personally like thought a lot about pruning it down yet. We're in a growth phase where we're just like rapidly trying to expand. But you're right, like one of the things we could do is look at like how popular certain features are within models. An idea that I have heard is to, I'm just like spitballing, by the way, is to look at like correlation between multiple features. If multiple features are correlated, maybe you can consider some candidates for dropping, but like I'm spitballing here. Haven't looked into it too much, to be honest. I guess the next question is, do you think that monitoring the quality of the engineered features is more important than monitoring the quality of the raw data? I guess, to be perfectly honest, there need to be solutions on all of the above. I think, yeah, I think you need to like have some monitoring on the raw data itself, of course, but you're going to go through transformations. You can introduce bugs in your data through those transformations. I'm not 100% sure if I would consider like one more important than the other. Feature quality directly, of course, affects your model quality. So if your goal is to look at your model performance and your goal is to look at like any leading indicators of model performance issues, then I would like, of course, put something down in the feature monitoring. Yeah, Danny?
Yeah. I'd say like yes, certainly if you're kind of interested in specifically a model performance, you're going to care a lot more about engineering features, kind of monitoring that quality, and that's also going to vary, right? Because sometimes you're going to have both batch sources as well as kind of stream sources, and stream sources kind of are notorious for having lower quality, right? And I think the tricky thing is how do you action on that, right? Some things are more actionable than others, right? Like you can say that maybe there's some feature drift in your engineering features and you need to just like retrain a model on that, right? That's kind of one action. But often it's you also need to have some sort of like fallbacks, right? Like you have like bad string feature values, fall back to the more stale version of this that you know is still good quality, right? So I think really it's when I talk to organizations, I typically recommend first focusing on the easier things here. So like kind of the raw data and the batch metrics that you can focus on so that you have clear actionable items. Once you kind of move into the streaming kind of land, that becomes quite a bit harder to kind of action on. Because there's always kind of a trade-off as well. If you want to kind of like block bad data, then you're inherently sacrificing on freshness of the features, right? So
And I guess if the question was I'm just in case the question was mostly from the point of view of batch data. So an example here is at Shopify, we're kind of leading the way in the feature store for data quality monitoring. But like any lessons we learn, any techniques we build, any tools we build, the hope is to like spread them out throughout. Because yeah, you should be monitoring your raw data sets also with similar tools, have some validation jobs set up that automatically go through rule sets and go through your raw data. I guess just like monitoring feature quality is a leading indicator of actual model performance issues, monitoring raw data is also, it just like reduces your time to detection even further. Yeah, just to like double down on that answer of like, why not both? I guess I'll move on to the next question. What incentives do you see working in larger orgs in encouraging feature store adoption? Would there be an adoption of incorporating the feature store in other tools devs use, GitHub, Azure DevOps, etc.? Yeah, I think in terms of like the stuff that I've already covered, the org will benefit from reducing feature engineering effort, duplicate feature engineering effort. But yeah, you have to kind of work on thinking through the ROI calculation that teams make and kind of try to add like more carrots along the way for teams to take on existing features instead of doing their own work. And yeah, some examples are data quality monitoring. Other examples are the online availability of features, like alerting teams about data disruptions. Any of these tools that you can think of are good ways to shift the incentives into using your tool. And then that eventually leads to, I guess, less duplication of effort. Not sure if that's kind of what you're getting at with the question. In terms of incorporating the feature store into other tools, yeah, that kind of makes sense. Like at least in our case, we do use like the actual feature store is in a GitHub repository. We do heavily use CI/CD for various processes for checking, like I mentioned earlier, that the tables that are registered in the feature store actually do exist, and they actually do match the schema of the feature view in your repo. I think those are good things that kind of increase the trust in the feature store a bit. Yeah, I'm not 100% sure I actually understood the intent of the question extremely well though.
Yeah, at least like for the first half of the question, I can give my 2 cents. So you often what I see in larger organizations is you have like maybe like a central ML platform team, but then you also have these like use case engineering teams as well that are powering their downstream data scientists. And so I think that actually the idea of a feature store that provides that abstracts away a lot of engineering complexity typically resonates actually fairly well with the engineering teams, right? So these use case engineering teams, the ML platform engineering teams. And so I haven't seen as much pushback on getting those kind of engineering teams to get adoption. It's really more like how do we, ultimately the data scientists are kind of the final kind of step in kind of making that adoption story stronger. And kind of we've talked a little bit about that in the past. But there's some sort of cultural aspect here as well. Like, are the data scientists incentivized to get like prod results quickly, right? And if they are, then then kind of all your stars are aligned and kind of everyone's incentives are aligned. But often that's just not the case, right? And so it's kind of a lot of it is like kind of not my problem. But there's also cases where that's not the case, right? And that's where you'll typically see the data scientist actually becoming an ML engineer to kind of speed up their kind of time to production, right? So I think it's happening. It's just slowly happening, and it's definitely starting from the engineering side and kind of bleeding more into the data scientists.
Yep. Cool. I think apart from some comments, that is the end of questions.
Cool. Thank
Thanks
you
for
all
attending.
so much.
And thanks, Danny.